Hi everyone. So in this video we are going to look at Markowitz portfolio optimization. So in case you have any idea about Markowitz portfolio optimization, it is an algorithm to generate a portfolio with maximum Sharpe ratio and also to plot the efficient frontier. As we go ahead in this video, you will know what is going on. But again, if you have some basic understanding, that's well and good. So moving on, we have a Jupyter notebook on the screen and we'll be calculating our portfolio with 4 stocks. You can increase this to as much as you want and number of stocks, but yeah, the algorithm remains same for everyone. So starting with the libraries, we will be importing NumPy as NP, Pandas as PD, Matplotlib for plotting the plots, Pandas data reader for collecting the data from Yahoo Finance, and this datetime module to specifying the dates. Okay, so we'll run this cell. Everything goes well and good. I have all the libraries installed. Defining the start and the end time to collect the historical data. Now this library or this algorithm collects the historical data and makes a portfolio on the historical time frame. So for that I have taken 1st Jan 2015 to 1st Jan 2020. So I'll change it to 2022. We are well beyond this timeline. So yes, collecting the data, we use data reader library and Yahoo Finance. We have specified Yahoo here. We have specified start date and the end date. So we are collecting for Bharti Airtel, Titan, Asian Paints and Pidilite India. So these are all the stocks that is listed on NSE India, and as per your location in anywhere in the globe, you can just find the ticker symbol on the Yahoo Finance, because we are drawing this data from Yahoo API, and then you can run this cell. So it will take a bit of time. So I'll show you this data what we have received. Yeah, so for each of the stocks we have received date, high, low, open, close, volume and adjusted close. We'll not be using any of the high, low, open and close and volume. We'll just use the adjusted close because it only needs the closing price for this algorithm. Going forward, we will concat all these data frames into one data frame and just the adjusted close. So we have this stocks, yeah, so here you can see we have date, we have the stock names as Airtel, Titan, Asian Paints and Pidilite India. Going further, we'll calculate the log returns. So for calculating the log returns, we use np.log. So NumPy already has the logarithm library, and we'll be doing shift 1. We'll be shifting everything by 1 and then we'll be dividing. So for every stock and every ticker point, we'll be dividing it by its previous value and then we'll taking the log. Okay, and also in the second line we are dropping the nan values. So we'll also have some nan values. Let me show it where it comes. Yeah, so in the first row you have seen that we have nan values because yeah, we do not have anything before first row, so obviously it will be not a number. So we need to drop it before moving further, just so that our algorithm doesn't suffer because of these nan values. Place, yeah. Now going forward, we'll be calculating the Sharpe ratio and plotting the efficient frontier using brute force method. So what is brute force method? we'll be specifying the number of iterations we are going to have, and then we'll be calculating randomly that what are the weightage of the portfolio. So out of this 4 stock, an equal weighted portfolio will have 25% allocation on each of the stocks. But when we are like talking about random numbers, and that too on a scale of like 5000 iterations, we can all the way range up to like 0. 0.5, 0.0, 0.05, 5%, 5%, and then like 40% and 40% allocation, and all the way up to like 90% in one stock, and 0.5% in another stock, and then like similar kind of like randomness. So why we are doing it? We are doing it because we just want to collect all the possible variation, not all the possible variation, that would be infinite, but most of the possible variations that we can have with the portfolio combinations, and then pick out the best out of them. So we are going for 5000 iterations, and in the following code we are creating containers actually. So containers actually make our code faster. So we are pre-allocating memory in case of like here we are like having zeros, so we are pre-allocating zeros to like return array, volatility array, sharp array, and weightage array. So once after running this cell, let me show you like what has been stored. Yeah, so we all have all the zeros values. So going further, when we calculate this, or when we have to store something in this return array, we'll just like take the location and store that value in this location. So this will make our code extremely fast, rather than like having a list and then appending it one by one. So the same thing is like for everything. Let me show you the weightage array. Yeah, I'll also show you the shape of this weightage array and then explain you why it is. So it is a matrix of 5000 cross 4. So why we have 4 values? Because we have 4 stocks, and each of the stock will have some kind of weightage. So for each of the 5000 iterations, we'll have the 4 weightages respective to each of the stocks. Now in the iteration part, we will be like taking randomly, generating random numbers based on length of the stocks columns. That is, we have 4 stocks, so we will have like 4 random values, and then we will be like dividing it by the sum of the weightage W. So the random number, when divided by the sum of random numbers, will scale it down so that the entire like combination of weightage, entire sum of the weightage will be equal to 1. So just to give an example, suppose like we have random number 25, 58, 96 and 114. Yeah, so if we like divide 25 we will be getting 8% or 8.53%. So similarly we'll be doing it for all the values. For 58 divided by the sum of everything, 96 divided by sum of everything, and 114 divided by sum of everything. So everything when we sum up, it will be equal to 1. Okay. To make my point, let me just do it in front of you. Yeah, so as you can see on the screen, we have 8.53% for the first one, 19.79, 32.76 and 38.90. so I'll also sum it so that it can be validated. Yeah, so I'm making the video a bit longer, but yeah, you can skip it out if you want. Yeah, so that's my point. So everything comes equal to 1. So that's the point of this summation, and this weightage we are going to store it weight array. So for each loop we are creating a 4 random variables, we are then scaling it down to 1, and then we are storing it in weightage array. Now this return array, so we will be like taking the sum of the returns, L return dot mean. So what is what is L rate? So L rate is the returns actually. So L rate dot mean, so mean return over the past 7 years of data what we have received from Yahoo Finance. So this returns we will be like multiplying with 252, that we have taken average number of trading days, and then we will multiplying that with the weight. So now you can like have a pretty brief overview that we are taking the returns for mean returns, and then we are multiplying it by the number of trading days in a year, so that we can get annual returns, and then we are multiplying by weight of those stocks. So Airtel, suppose it gives me 4% returns in a year, and then I multiply it by the weight of the returns, so that we can get the portfolio's returns, and that we are going to store it in returns array. Similarly for volatility array, but in volatility we cannot directly, so we are going to take annual volatility, and to take annual volatility we will take pairwise covariance, and then we'll multiply it by 252, that is our number of trading days in a year. Then we'll take the dot product along with the weights, and then multiply it, then again we take a dot product with the weightage. So the thing is, you can view it like this: we cannot directly calculate the volatility of a portfolio, so we have a formula. So you can go and like Google it out, the volatility of a portfolio, and then you will get a similar formula actually. Now the last code line here calculates the Sharpe ratio. Now the Sharpe ratio is kind of the returns divided by the volatility. So this is kind of going into loop for all the iterations, that is 5000, and then we are going to calculate, then we are going to fill the arrays what we have declared in the previous cells actually. So these arrays, return arrays, volatility arrays, Sharpe arrays, and weightage arrays, these are going to be filled in this cell. So for 5000 arrays it will take some time, but it should be over soon. Yeah, so we have all the blank arrays, now they have been filled. So let's check. Yeah, so you can see the weightage array, return array, everything is filled. Now this result what I have stored in RES, that is the maximum Sharpe ratio that can be like formulated with the combination of 4 portfolios. So what is coming out? Yeah, so it's 1.13. Now in the final section we will plot whatever we have collected the data, and we'll present it in a presentable format. So if we run this cell, you can see that this is the efficient frontier, and the Sharpe ratio is highlighted by the CMAP graph. The more yellowish or more brightish the part, the higher the Sharpe ratio. The maximum Sharpe ratio can be observed as 1.1357. So yeah, so this is the entire Markowitz portfolio optimization. There are multiple variations to calculate this optimization problem. This is kind of a brute force. There is also an mathematical computation method on which you do not need to have this kind of brute force. So we'll see it later. Okay, so in case you are like you have any queries, you can just comment it down, or you can reach out to us. Thanks a lot.